All right, good afternoon. If your bell work has popped up, you will see that the directions say to use your GeoGebra and try to model the information given to you in the chart, meaning you should plot some points, take a look at what those points look like, and then use your fit feature, which we've done multiple times this year when you type in FIT, and then you can fit to lots of different types of functions, right? And I think specifically this one is saying, is it linear, exponential, or logarithmic? So fit line would be linear, fit exp would be exponential, and fit log would be fit logarithmic. I would recommend, you don't have to do this, I would recommend that you use your spreadsheet and enter in numbers, your data over here. That way you don't have to type in A, B, C, D every time you do a fit. Does that make sense? So what I did is I used my spreadsheet view. I punched in all the data in columns A and B. And you guys might remember, if you highlight everything and right-click on it, you can make create list of points. Create list of points. And then that's how I got this green L1. That way I have them all in a list and I don't have to type them in individually. Let me know if you're having issues with anything. Now, once you get the data graphed, just the points plotted, you should have a screen that looks something like mine. You can probably answer the question to your quiz without even doing the fit, if you understand the difference between a linear, an exponential, and a logarithmic. When you believe you have it, go ahead and finish your quiz. Did you ever figure out your OneDrive thing? Because we're still trying to get you to share a bunch of documents, right? Is it working, you think, now? Like if I were to go in there, would I be able to see those GeoGebra files and stuff? Because I think we're still missing grades from like all the way back to the used car, right?
Yeah.
Okay. We can take a peek at that right after class if we need to. You should be able to get the data from, do you have your Blackboard quiz open? Like that's where you're punching in the dots from, right?
Yeah.
And then you say
So can you fit a function, and which one do you think it's going to be? Like what shape does it look like? Does it look like a straight line? Does it look exponential, or does it look logarithmic? It's not a straight line. Yep. So you might recall from the other day we talked about the difference between a exponential and a logarithmic. One starts out slow and then goes fast. One starts fast and then goes slow. So which one is it? Everybody got their data plotted? You can try all three of them. If I wanted to do fit line, I'd type in FITLINE. My list of points is L1. Remember, if you have is this where if you have a Mac, you have to do L_1? Yeah. So if you have a PC, you can just do L1. So I can do a line. Okay, it's not the worst fit in the world, right? But it's not perfect either. And then my other one is fit exponential, L1. That doesn't even work. We can talk about that, why that is, in a second. And the other one is fit log. Much, much nicer, right? So I'm going to turn off this line. You should have found that the fit logarithmic was basically perfect, right? It fits very nicely. So if you were listening when I was talking a second ago, you'll remember that we talked about the difference between an exponential and a logarithmic. I had this up on the PowerPoint the other day. An exponential starts out growing how? Slowly, and then eventually gets fast. It's like Avi and Bonita in that daily pay one. Remember the one penny, 2 penny, 4 penny, 8 penny, but eventually the exponential growth took off and it went really fast, right? So if exponential starts slow and goes fast, then a logarithmic starts fast and eventually slows down. They're inverses of each other, right? And of course, what does a straight line do? Doesn't start slow, fast, change. It's constant. It's a straight line. The slope never changes, right? So a straight line would look something like that. So obviously this one is logarithmic. So what we're going to do here, the exponential. When you try exponential, do you see how it doesn't work? The reason it doesn't work is one of our outputs is a 0. One of our dots is a 0. And what did we say about exponential? Our base has to be a positive number. Can't be 0, right? Positive number can't be 0 and it can't be 1. Well, you can't take a positive number raised to some exponent and get 0. So the fact that one of our dots was at 0 kind of tricked the computer. It's like, well, we can't do it because we can't have that 0 there. That's why that didn't work. I think if I adjust that to like 0.01 or something really close to 0, then it'll actually do it. Do you see how I just adjusted that dot a little bit and then I just had to get rid of the 0. But obviously that green one is exponential. That doesn't fit our data at all. That's way off, right? Comments or questions on that? What I would hope you would be able to do is understand enough about exponential, logarithmic, and linear growth to look at that, and without even thinking, in like half a second you can say, oh, that's logarithmic. It's got the logarithmic curve that has that look to it. Okay, so I hope you got 2 out of 2 on your quiz. If you haven't submitted yet, you should do that. We're going to practice a few of these with our computer today. So this is the one that you just did, find the model. Did you notice that when you do fit log, the computer automatically goes to ln, natural log? That's the default on your GeoGebra. The same thing when you do fit exponential, it's automatically going to go to the e as your base. That a equals a naught e to the kt. That's the default on GeoGebra. Okay, let's check out this one. Now, I know it gets really tedious punching in a bunch of dots. So what I did on Blackboard, if you go to Blackboard and you go to Course Docs and Links, scroll down to 6.7, 6.8, there's our Empire State Building. right underneath the Empire State Building, I have GeoGebra files for 673, 74, 75, and this the cell phone one that we're going to do a little bit later. So I already created these four for you. I plotted the points for you. So you didn't have to spend all your class time plotting points, okay? So what I'd like you to do is open up that 6.73. And the 6.73 goes with this data. It says a university study was published investigating the crash risk of alcohol-impaired driving. Data from crashes were measured against your blood alcohol content with the risk of being an accident. The relative risk is how many times more likely a person is to crash than a person who hasn't been drinking at all. So we got X and Y values here, right? The X values will be your blood alcohol content, so 0, 0.01, 0.03, blah, blah, blah. The Y values would be your relative risk of crashing. I know that's kind of confusing. What they're saying is, if you have a blood alcohol content of 0, your relative risk of crashing versus a sober person is 1 to 1, because you also are a sober person. Does that make sense? So your relative risk of crashing is 1, meaning you and the other person have the exact same likelihood of crashing. But notice, as your blood alcohol content goes up, so does your relative risk of crashing. So if you are a 0.21 blood alcohol content, you have almost a 100 times more likely chance of crashing than the person who is a 0 blood alcohol content. Does everybody have their GeoGebra open? It says let X represent the blood alcohol content, Y is the relative risk. The question says after 6 drinks, a person weighing weighing 160 will have blood alcohol content of 0.16. How many more times likely are they to crash? Okay. So, let me open this one up so I'm on the same one as you guys. Here's the data that I punched in for you. Whoops. Sorry. Okay, here we go. Here's the data that I punched in for you. So, you should be able to look at that, and without even using your computer, you should know what type of relationship is going on there. What is it? It's exponential, obviously, right? It starts slow, and it starts to grow quickly. So what I want you to do is I want you to find the best fitting function for that. How are you going to do it? Fit, F-I-T. Fit who? EXP, exponential. My list of points again is L1. And you can see that your computer is going to give it to you in terms of E. So again, look at the 0.58 E raised to the 23.82x. You'll remember the equation we worked with on Friday is the final amount is the beginning amount E to the KT. So here, our computer uses X instead of T, right? The K, that's 23.82, is our, if it was money, it would be the interest rate. 23.8% if you want to think in terms of money. So like the rate, E is just E. A naught is the beginning amount, which we already said the beginning amount was going to be 1. And they're saying it's 0.58. So again, this model doesn't hit every dot perfectly. Do you see what misses some of the dots? It's not a perfect fit. It is the best fit for a exponential. And specifically, you can see it misses J, K, and L. Does everybody have a similar graph to mine? Should actually be identical to mine. Okay? Now, one fun thing to do is, not that we're doing this right now, but you can just see how changing one point like messes with it. So like if I grab point J, for example, Like what happens if J was like here? Do you see how my graph moves with it? Because it's taking into consideration all of these points. So if you move a point around, I'm going to undo that so it goes back to where it was. Remember, your green function is defined to fit all of those points. So if you start changing points around, it's going to change your function around. Okay, so it said the question was we want to solve for the blood alcohol content of 0.16. Notice nowhere on our data do we have a 0.16. We skipped it. We went from 0.15 to 0.17, right? So this is just like the used car activity. It's just like all these other interpolation and extrapolations that we've done. We get some data. We figure out what kind of function it fits. In this case, it's an exponential. And now we can use that exponential function to solve for some data that we don't already have, namely 0.16. So how would I figure out what 0.16 blood alcohol content corresponds to on my computer? F of 0.16, yeah. Just have it spit it out. And if I even want to see the dot, I'll do a point. I'll do 0.16, comma, F of 0.16, and it produced for me a new dot called M, and it's saying that this person would have about a 26 more times likelihood of crashing than the person who had a 0 BAC. How do you guys feel about that? Let me share one other nugget of information with you. I used my computer. I didn't do any mental math, no paper pencil, no calculator, nothing. I just used my computer to spit out that point, correct? What happens if I would have just taken my calculator and punched in 0.58, go ahead and try it, 0.58 times E raised to the 23.82 times, my X is where I'm going to put my 0.16, right? 0.16. I get 26.218. But my computer gives me 26.35. Anybody else get 26.218 when they did that? So who's correct? Is it this calculator or is it this computer? Why one of them's wrong? Any idea why they're different?
Is it because GeoGebra is trying to fit it?
It's the same function. They fit it, and they fit it with this function, and this is the same function I punched in my calculator, or is it?
You're rounding on GeoGebra.
Yeah, this is rounded. 0.58, 23.82. I currently have my GeoGebra set to round to 2 decimal places. So if you go to options rounding and change it to say like 4 or 5, I'll change it to 5. Do you see how it's not 0.58? It's actually 0.58305. And it's not 23.82, it's 23.81758. So when I punched it into my calculator, I was just using the 2 digits that my screen was showing me. But when I have GeoGebra do it, regardless of how I have the rounding set, it's using all of the decimal places, as many as it does, like 19 or something like that, even though it's only showing 2. Does that make sense? Some of you did that on your used car activity, where your computer would say one thing, but your paper and pencil calculations, if you pulled out your calculator, would say just a little bit different because one you rounded and one you didn't. So just thought I'd share that with you. Not a huge deal, but just be aware of that. So that was a fit exponential, right? Let's try the next one, 6.74. So go ahead and open it. I'll show you the data that it comes from. It says, due to advances in medicine and higher standards of living, life expectancy has been increasing in most developed countries since the beginning of the 20th century. This data shows life expectancies for Americans from 1900 to 2010. Notice again that it's going up, right? Back in 1900, we were only expected to live till we were 47.3 years old, which isn't very far away for some of us. But now notice, if you go all the way to the year 2010, the average life expectancy is 78.7, right? Better doctors, better medicine, vaccinations, all that kind of stuff. So, go ahead and open your file, 6.74, I think, right? The question is, what type of growth does that look like to you? I want you to try a bunch of different ones. Try as many fits as you want. Fit line, fit poly. Remember, that's a polynomial. You can do like a second degree or a third degree. Fit exponential, fit logarithmic. Try whatever you want. See if you can find the one that you think best models the data. Notice that they had us doing a goofy labeling on this one. X equals 1 refers to 1900, and then they go in decades. So 2 is 1910, 3 is 1920, and so forth. So I think 12 was the year 2010. Is that correct? 1900, 10, 20, 30, 40, 50, 60, 80, 90, 2000. No. Did I screw that up? Now I'm a little confused. We went from 1900 to 2010. I should have 12 dots. Do I have 12 dots? 1900, 10, 20, 30, 40, 50, 60, 80, 90.
You keep skipping 70.
Did I skip 70? I can't even count by 10? My goodness. Let's try this again. 1900, 10, 20, 30, 40, 50, 60, 70, 80, 90, 2000, 2010. Good grief. I'm pretty sure counting by tens is either a kindergarten or first grade standard, so I might need some review.
It's the end of the semester.
Yeah, thank you. Does anybody think they found a good fit? What do you think, Jordan?
I did longest.
Logistic. Wow, we haven't even pulled that one out yet. So you guys found the logistic one. Let's talk about that one later. Fit poly. So you did a second degree. Let's. I'm going to come back to that one, Jordan. Let's. Hannah's saying fit poly 2, which is a quadratic parabola, right? So if I do fit poly, and I'm going to do list 1, comma 2, do you guys think that's a good fit? Any thoughts on that?
It's going back down a bit.
I think it's a good fit if I put my blinders on and I just look from here to here in between those two marks. I think that's not bad, right? So I think we're good if we decide to interpolate, meaning make predictions within the boundaries of those two red lines. But the question is going to say, use the model to predict the American life expectancy in the year 2030.
I think it's more linear.
Yeah, so before we go there, is this going to be a good one for 2030? Well, this was what, 2000 what? 10? 20? I don't know, that's not bad, right? Because it hasn't started going down yet. But what about 2090? Are humans going to start dying younger? I don't know, maybe. But eventually this model is going to not work, eventually, right? Because look what happens if I scrunch it over. I mean, they're basically saying by this time we're not going to have any life expectancy at all. And we know that that's not the case, right? Okay. So I think that's a good model, but there's other ones. There's no correct answer here. Okay, this is just about being able to analyze it. Who else had a model? Somebody said linear?
I said linear based on the fact that on the data that each year it increases. So if you base it off of the data, it's going to continually increase each year.
So yours looks like that?
Yeah.
Now, just because it increases each year, does that mean it's linear? I mean, I could do a line that increases, but can't logarithmic and exponential and everything else also increase each year? It's just that they don't increase by the exact same amount each year, right?
It's not increasing slowly or
Or quickly? Yeah, so I could see where you could make an argument to say that this is linear. And if you did make this argument that this was linear, if we went out for 20 years, that would get me over to 14. And our life expectancy would be shy of 90. Yeah, 80s something. So linear, not bad. What else did we try? Anybody try exponential? How did the exponential look? Fit EXP. Do you guys believe in that? I don't know if medicine is that good. Is our life expectancy going to be 110 in the next few decades? That might be a stretch, right? I don't know about exponential. Did anybody try logarithmic?
Yeah.
How did that look?
It was okay.
Fit log. Does that seem realistic? It's still going up, but it's not going up super fast, right? Like if we go back to, I don't know how many years back, I'm not a history major, but at some point we discovered a vaccination for like polio or something, right? So there was a curve where life expectancy was growing really fast and now it's tapering off a little bit. So again, there's no correct answer here. You could use any of those models. If Hannah uses quadratic and Luke uses linear and somebody else uses logarithmic, all three students are going to get three different answers, right? Doesn't mean one is more correct than the other. It's, do you understand the concept behind what you're doing? So if I look back at our original question, it actually says in part A, use logarithmic regression. So the question is saying, hey, this is probably a logarithmic. So if we were following the directions, we would just use the logarithmic one, right? Comments or questions on that? Going once, going twice? Okay, this one I'm just going to have you try on your own. This one is 6.75, so you can open up the data if you want. I'm not giving you any directions on this other than asking you to solve what's in the yellow. I say predict what percentage of Americans have cellular service in the year 2019. So notice our data only goes to the year 2012. So we're going to make a jump of 7 years at the end of our data to make a prediction. I don't care what model you use, but try to convince me that you know what you're talking about. So go ahead and try it out. So there's your starting point, the data that I plotted for you. It's up to you to figure out which model you want to use. Now use a little bit of common sense too. Take a look at the labels on your variables and try to solve this within the context of what we're actually doing here. Do you guys all remember your first cell phone? Do you remember what year you got it in?
I know what age I was.
I got mine in 1998. I was one of 25% that had a cell phone in 1998. Does that mean I'm advanced ahead of the curve? Might have been 99. You want to see the data again? So the only thing that's on here is it says mobile telephone service has increased rapidly since the mid-1990s. Today, almost all residents have cellular service. This one shows the percentage from 95 to 2012. So we got every single year from 95 to 2012. And then I erased the rest of the question. Then I just typed in the yellow there. Predict what percentage of Americans have cell service this year, 2019. Does anybody have a prediction?
Yep.
What did you predict?
112.8.
112%?
100% is a lot.
Taya?
100%.
Why are you stopping at 100%?
Because you can't have more. If you have 20 people, you can't have more than 100%. It's 100% is like everyone.
Correct. So the reason I give this to you is because you very well could have come up with a model. I'm going to draw in a line at 100. Y equals 100. You very well could have come up with some kind of function that went above that black line. But Taya knows what she's talking about because she knows that it's impossible for more than 100% of people to have cell service. Like, isn't 100% our threshold? Right? This is one of my pet peeves, by the way. Any of you who are in athletics at all have ever coached or have ever had a coach? Have you ever had a coach tell you we need to give 110% tonight?
Yeah.
Okay. The next time your coach tells you that, say, Coach, Dr. Worth says that is mathematically impossible. Because it is. Right? You can't give 110%. All you can give is 100%. Marcus, only ever dropped that on you? He's actually said 110%? Yeah? Montgomery ever? Yep. Tell him he's wrong. He's wrong. Okay? Okay. Who thought they had a good model here? What was a good fit model? What did you get, Hannah? Logistic again? Okay, everybody, let's try the logistic. First of all, remember when we said exponential starts slow and then goes fast? And logarithmic starts fast and then goes slow? The logistic is kind of a combination of the two. It starts slow, it looks exponential at first, starts slow, starts getting fast, but then at some point it slows down and then it turns into a logarithmic. Do you see where I kind of halfway through I switch gears a little bit? Half exponential, half logarithmic. That in a nutshell is what logistic growth is. Okay? So some of you found it on your computer. It's called Fit Logistic. Fit Logistic. Do you see how it's kind of a half and half? It looks like an S, right? It looks like it's exponential at the beginning, and then right around point Hij, it kind of switches, and then it goes logistic. Does that model make sense? Other than the fact that it goes above my 100, does the model make sense? Yeah. So again, we would have to proceed with caution here. We know we're not going to go over 100, right? So if you look at the logistic, go ahead and see your equation. Does everybody see it at the very bottom? It should say 105.74 in the numerator. That 105.74 is kind of like your ceiling. It's never going to get to 105.74. So what's our actual ceiling going to be here? It's going to be 100. See, GeoGebra doesn't know that we're talking about percent of people. GeoGebra doesn't know what this data is. It's just a bunch of data, right? But in the context of what we're doing, we know that our ceiling has got to be 100. So you could actually even change it. Well, I'd have to retype it in. But I could retype it in as 100 divided by 1 plus 25.2 e to the whatever. And it would then keep it under 100. It might not fit our data perfectly, but it would it would keep us underneath that ceiling. So I don't know, what's a good prediction for 2019? 100% or maybe just shy of 100. I mean, there's got to be somebody out there that doesn't have cellular service, right? So 99% or something like that. So I guess the moral of the story when we're doing fitting of functions like this, don't try to think that somehow the math that we do is going to give us some perfect answer to every scenario, because sometimes there's scenarios that can't be explained with a simple formula, right? You have to use a little bit of common sense like Taya did when he said, well, we can't go over 100%. So, comments or questions? Do you guys remember doing the Desmos activity a few weeks ago where we plugged in our cell phone and we charged it? Yes? And almost all of us got a bad prediction at the end of that activity because it looked like it was going in a perfectly straight line. So we all predicted that it was going to get to 100% charge following that same straight line, and then we all found out that we were wrong. Right? I plotted that data. Go ahead and open the 6.8 Desmos cell phone charge data, GeoGebra. It's the last one on our list. I actually plotted that data, and here's what it looks like. Now, when we did the Desmos, it kind of stopped us about like right here. Or I can't remember where it stopped us. So it made sense that it's like, oh, you know what? It's just going to go like that, and we're going to hit 100% right there, and we all got it wrong. So now using that data, now knowing what we know, can you find a function that fits that data? Go ahead and try all your different ones. And don't try ones that you know aren't going to work. For example, that is not exponential growth, right? Yeah, and it's linear, but we found out that it wasn't going to stay linear very long, right? And now that you have a new member of your repertoire here, our friend Logistic. Anybody try that yet?
Yep.
Not bad, right? Yep. Not bad at all. Now, we know that eventually the cell phone is going to get to 100% charged, right? Go ahead and look at your equation. What's it given us as a ceiling? 99.14. So is it a perfect model? No, because our very last dot actually was 100%, but it's really darn close, right? So again, all it is it's not a perfect fitting model, but you could call it maybe a best fit model. So what I would expect you to be able to do on like a test or a quiz or anything like that is maybe I give you some data table. It doesn't matter if it's years or blood alcohol content, or it doesn't matter what the data is. The labels are almost irrelevant, except for when you have to use a little bit of common sense to relate it. I would be able to give you a chart, something like this. And let's say I cross this number out. Could you make a prediction as to what number you think would have gone there? How would you do it? Graph it all. Graph all the data that we have. Find a function using your fit that looks like it fits. And then use that function to punch in 1999, whatever that is. And you could make a prediction for what you think that number would be. That would be called interpolate. That's a fun word to say. Interpolate. Notice it is inter. It is inside of our data range. 95 was our first dot. 2012 was our last dot. So any dot in between those two is on the inside of the data, right? If we make a prediction to 2019, that's outside our data, because that's past 2012. Or if we went back to 1994 or 93, that would also be outside our data. Then we say extrapolate. which is another fun word to say. Notice that extra exterior, it's on the outside. So either way, whether I give you an interpolation problem or an extrapolation problem, you should be able to make a prediction with your functions. Okay, here's our schedule going forward. We are only going to spend one day on section 7.1, which is on Wednesday. We're going to work with solving systems of linear equations, which you have all done before in Algebra 1 and Algebra 2, but we're going to spend the day reviewing it. Substitution, the addition or elimination method, how we can solve for two variables and two equations. And I'll give you a couple application problems on that, and then of course there's an OpenStax quiz on that. Wednesday's our last day of regular class. On Friday, you're going to take a test on just Chapter 6 and that one section of Chapter 7 that we're going to do on Wednesday. And then during finals week, I can't remember what day our final is on. Thursday, we're going to take a final test that covers the whole semester. And all of our regular tests are worth 50 points, right? The final is worth double that. The final is worth 100.
I have two questions. How
Yep.
many questions is the final?
I don't know.
And,
It'll easily fit inside of 2 hours. That's the time block that we have.
and I realized that you updated that chapter 6 and 7 are already available. Is there any reason that you made it?
I made it available for online students. Yep. Some of the online students are ahead of pace, so they might take the test before you actually do. But it's password protected, so even if you clicked on it now, you wouldn't be able to get into it. But as far as I'm concerned, you guys will take it Friday at 1 o'clock. Yep, good question. Any other questions before we're out of here today? All right. Have a good one. See you on Wednesday.